Hey, what's up YouTube? In this video, I'm going to showcase a system for creating simple effects that can be sampled in, say, your grass shader, particle systems, and more. It's not groundbreaking, but it's straightforward and can get the job done. That said, it's not really scalable, so don't expect too much. It's a quick and dirty solution that can help you get started, and in some cases, might even be enough on its own, depending on what you need. But if you're expecting hundreds of actors all spawning dozens of effects, this approach won't cut it. Alright, let's dive in. So the overall idea is to create a pool of effects, let's say 16 of them. Each effect will be described by the following properties: its 2D position, a timestamp representing the game time when the effect was spawned, its duration in seconds, its radius in centimeters, its strength expressed as a displacement in centimeters, its direction expressed as an angle in radians, and its cone angle expressed as an angle in degrees for convenience. Now, this setup is somewhat arbitrary. You could structure it differently or even use a 3D position instead of 2D, for example. It really depends on your needs. All of these parameters add up to 8 floats in total, which conveniently fit into 2 float4 or vector4 values. With this pool of effects, the idea is to use a circular index to spawn new effects. That means each time you spawn an effect, you increment an index. Once you reach the 16th effect, the index loops back to 0, recycling the first one. Alternatively, you could manage a variable-sized list that only keeps track of currently active effects, but that approach adds extra complexity. For today, a fixed size pool will work just fine. Of course, this comes with some limitations. Spawning too many effects too quickly might cause you to recycle an effect whose lifetime hasn't yet expired, causing all sorts of issues. It's something to keep in mind, but with a large enough pool, reasonable spawn rates, and effects that don't last too long, it's usually not an issue. Now, the goal is to sample this data, this pool of effect, on the GPU, and I'm going to demonstrate 2 possible ways to do that, though there are certainly more. For example, you could simply use a material parameter collection and store 2 vector4s per effect to list them all, then access each vector individually in a material. But that approach has its limits. Adding new effects to the pool becomes a pain, it's tedious to manage in shaders, and it doesn't easily extend to other systems like Niagara. Sure, you could link a Niagara parameter collection to your material parameter collection, but that's still a very manual and error-prone process. By the way, this is somewhat similar to the method I used years ago to create one of my grass interaction systems. Instead, I'll show you 2 more flexible methods: how effects can be rasterized and quote-unquote baked into a render target, and how they can be stored in a texture as a lookup table, allowing you to iterate and sample them anywhere a texture sample is available, whether that's in shaders, Niagara, or elsewhere. I'll demonstrate the lookup texture method first. For either approach, we'll need a bit of logic on the CPU side first. I've gone ahead and built a blueprint actor component. The effect pool is stored as a float array. As I mentioned earlier, I could have used a vector4 buffer and stored 2 vector4s per effect, but using a float array is generally less restrictive, especially when dealing with data structures that don't fit perfectly into vector4s. You do you. In my case, each effect consists of 8 floats, so the first step is to resize the array to accommodate the correct number of effects. This happens in that init function, where I can specify both the number of effects to store in the buffer and the attachment actor, which will come into play later. Once I know how many effects I need, I simply resize the array to hold 8 floats per effect. Next, since I'm going to use Niagara to either rasterize these effects or store them in a lookup texture, this blueprint actor component needs to reference a Niagara actor that owns a Niagara system component. And so this next function is a bit over-engineered to handle cached references, but the key part is this. I simply spawn a Niagara actor, cache its reference, access its Niagara component, and cache that as well. and then I set the system asset. After that, I provide a Niagara with the number of effects and the number of floats per effect. I also attach the Niagara component to the desired component. In my case, this blueprint component is attached to my character. And so I want the Niagara component to be attached to the character's root component. That way, the Niagara system's position automatically reflects the character's position, and this becomes important later when rasterizing effects. Anyway, next I initially disable the rasterizers and lookup texture emitters in the Niagara system, and then I reinitialize it just to be safe. So that's the initialization part, nothing too fancy. I'm simply setting up the array size and spawning a Niagara system that I can easily access from this blueprint component. Now, from the user's perspective, once this component has been initialized, all that's left to do is call its spawn function and provide the necessary arguments: 2D world position, 2D direction, duration, radius, angle, and strength. 8 floats in total, just as expected. So let's have a look at that function. The first step is to compute the offset in the float array where we want to write that new effect. Since each effect uses 8 floats, updating, say, the second effect means starting at the 9th float in the array, so index 8. Next I perform a quick safety check and then I simply update the array values. X and Y position first, then the timestamp, duration, radius, direction, cone angle, and finally strength. After that, I increment the effect index and make sure it wraps around. So when it reaches the pool size, it loops back to 0. Then I send the updated array to Niagara and enable the required emitters. And these emitters stay active only for as long as needed. For example, the rasterization emitter only needs to run for the duration of the effect, while drawing the lookup table takes just a single frame, so that emitter can be disabled on the next tick. And that's pretty much it for this blueprint. All it really does is manage a circular float buffer, send that buffer to Niagara, and activate or deactivate the relevant Niagara emitters when needed. Thus, most of the magic happens in Niagara. First, this Niagara system includes a few user parameters that can be set from blueprint. Specifically the float array named effects, which gets updated in blueprint, as well as a number of effects and floats per effect. It also has texture render target user parameters that point to, well, the actual render targets. Alright, so let's start by looking at how the lookup table is rendered. In that emitter, when the emitter spawns, I create a render target 2D parameter at the emitter level. This parameter points to the lookup texture render target. I override its format to RGBA32 float and set its filter mode to nearest, which is very important. Next, I use a simple custom module to set the texture size. In this case, I want the lookup table to be as wide as the number of effects, and since 8 floats can be stored in 2 RGBA pixels, the height only needs to be 2. So it's a tiny render target, right? The rest happens in a simulation stage, which dispatches a compute shader once per effect. Inside that custom module, I sample the float buffer at the appropriate index to access the X position, Y position, timestamp, duration, and so on. Then I simply store these values into the rows of the render target dedicated to each effect. Since the compute shader is executed once per effect, the execution index corresponds to the effect index. And so I simply write the 8 floats into the top and bottom rows of the render target, 2 sets of 4 values per effect. And that's basically it. Since my character calls the spawn function on left click, I can keep clicking left-click in-game to spawn effects and watch the lookup texture update in real time. 1, 2, 3, 4 and so on. You can clearly see the circular buffer in action as it loops back to the first effect again and again. Cool. Now the final step is to sample this lookup texture to, so to speak, render these effects. By sampling the 2 pixels in a given column, we can retrieve all of that effect's data. From there, knowing the effect's world position and radius, we can create a sphere mask from any world position. Next, by comparing the effect's spawn timestamp with the current game time, we can determine how much time has passed since this effect was spawned. If that value is negative, we skip the effect. Otherwise, we divide the elapsed time by the effect's duration to get a normalized lifetime value in the 0 to 1 range. Kinda like a particle. 0 at birth and 1 at death. If it's greater than 1, we skip the effect as well. With that 0 to 1 lifetime value, we could sample another lookup texture to drive a curve, for example to create a fade in and out with a spring-like animation. Or we could simply compute such a curve mathematically. Next, using the effect's direction, stored as an angle in radians, we can reconstruct a 2D unit vector with basic trigonometry to get its world space direction. That can then be compared to the direction from the sampled position to the effect's origin. Then, with the effect's cone angle, we can compute a cone mask. If we want a spherical effect, setting the angle to 360 degrees will do that. Otherwise, we can narrow the cone for more directional effects. And by combining these masks, distance, time and direction, we can compute the effect's 2D displacement at any given time from any world position. Do that for each effect, sum the resulting displacements and voila. That's the theory. Now let's see the implementation. Here's my grass shader. This texture is the effect's lookup table, and the number of effects corresponds to the texture's width. The world positions at which we sample the effects are the grass pivots, converted from local to world space. Baking and sampling pivots is something I've explained several times on this channel, so I won't go into it again. For each effect, I compute the row's U coordinate used to sample the lookup table. I sample the top pixel and then the bottom pixel to access the effect's data. Next, I compute the position delta between the effect's origin and the grass blade's position. This value is multiplied by the inverse radius, then inverted, 1 minus, to create a spherical mask. 1 up close and 0 at the effect's maximum distance. The cone fade is a bit more complex. It starts by converting the direction from the grass blade's position to the effect's origin into an angle in radians. Then there's a bit of math to account for the effect's direction and cone angle to form the cone fade. It's not particularly interesting. Finally, the time fade is a simple spring oscillation using cosine modulated over time with an exponential decay. I'm not too happy with this implementation since it doesn't properly respect the effect's duration. The spring fadeout isn't really tied to the effect's duration and might still be running once the effect's time has ended. But whatever. It's also faded in. The direction from the grass blade to the effect's origin, multiplied by all these fades and the effect's strength, gives a 2D displacement vector that's accumulated across all effects. The grass tips are then simply offset by that amount, while keeping the roots fixed using a top-down gradient baked in UVs. Then, to fake a rotation effect, I use a spherical reprojection, which, by the way, gives me a direction I can use to adjust the normal if needed. I covered spherical reprojection in detail in my stylized grass video. Anyway, tada, the grass is moving. And that's essentially why this approach isn't very scalable. It basically involves a for loop with quite a few texture samples, potentially per vertex, depending on your use case, so there's a performance cost. For around 16 effects, and depending on your vertex count though, it's usually fine, considering such a tiny lookup texture will likely stay fully cached. It still comes with a non-negligible cost. As always, when in doubt, profile on your target hardware and see for yourself. Anyway, this can be replicated in, say, Niagara, for instance. The HLSL code can almost be copy-pasted, although the way to return a value is different in Niagara, as well as the texture sample function. But yeah, you can sample the effects to, say, add a force, and along with gravity, rotational drag, collision and whatnot, you can create very cool effects. This effect shares many similarities with one I showcased in a previous video, where I used Niagara's rigid mesh collision interface to create some very cool effects. Anyway, that's the first solution. The second solution would be to render each effect, but this time for every pixel in a render target. Each pixel would be given a world coordinate that fits within a certain area in world space, and you'd run pretty much the same code. The result would be a render target that looks like this. You'd then simply sample this texture in your grass shader, Niagara system, or whatever you're using. Now, before going any further, I'd like to highlight the potential pros and cons of each technique. For both solutions, the CPU cost can be negligible. Right now, that's not really the case since this is a blueprint implementation, but converting it to C++ would be fairly straightforward, and once that's done, the CPU cost would become practically negligible. On the GPU side, rendering the lookup table itself is cheap. The main cost comes from Niagara's overhead, and I bet converting it to a simple compute shader dispatched in C++ would make it even cheaper. Spoiler alert, I've already implemented that, so stay tuned for the results. What is costly is sampling all the effects stored in the lookup table. That's 2 texture samples per effect, plus some math for each one. In a particle system, that's not necessarily a big deal, since it's done once per particle, but in a vertex shader the cost becomes noticeable. And it adds up fast. If I set the effect count to something large, say 128, you can see the performance start to drop in this particular scene. Each vertex ends up performing 256 texture samples. And even though the lookup table is small and probably fully cached, it still has a cost. The benefit of this technique, however, is that it opens up a lot of possibilities. As I mentioned earlier, effect positions could be stored as 3D coordinates in the lookup table, allowing you to compute sphere masks in full 3D space, with the Z component taken into account, instead of only using 2D plane coordinates. That could be really useful for properly spatializing each effect. Also, since the effect's time is computed on the fly, you can do interesting things, like slightly offset the time along the grass height. This creates a subtle delay in the animation, which looks pretty cool. Another thing to keep in mind is that outputting velocities is extremely important nowadays, with all the temporal effects like GAA and others. And this is done by computing the world position offset from the previous frame. And when you're using any time-based effect, this is automatically computed for you. Time is internally replaced with time minus delta time to compute the previous frame's world position offset. It's all taken care of. The memory footprint is also tiny. A 16:2 texture with 32-bit floats is practically nothing. That's the lookup table method. Now let's talk about rasterizing the effects to a 2D texture. The rasterization pass itself is fairly cheap, and even with a large number of effects, it wouldn't cost much, assuming the render target size remains reasonable. Sampling the rasterized effects in the grass shader or in Niagara would also be extremely cheap. You'd just convert world coordinates to unit space and do a single texture sample. However, what's baked into the texture is baked. For instance, adding a time delay along the grass height is no longer possible, at least not directly from this baked texture. Once it's baked, the effect's time can't be modified, and you can only sample the sum of all displacements. That being said, there are solutions. You could rasterize the effects to another 2D texture with a bit of time delay, but it comes at a cost, extra memory footprint and so on. Moreover, outputting velocities becomes a bit tricky. Since this isn't a time-based offset anymore, there's no live time variable, right? Computing the previous frame's world position offset for the velocity buffer can only be done using a double buffer. That means you'd rasterize the effects into this render target, but before doing so, copy it to another render target and use the previous frame switch node. So you end up with 2 textures and 2 texture samples. It's still fairly cheap, but the memory footprint is significantly higher than that of the lookup texture method. So as usual, there are pros and cons. Choosing the right method depends on your use case, expectations, memory budget, performance, and whatnot. Finally, using the lookup table method allows you to sample effects both up close and at far distances, whereas rasterizing effects is spatially limited. Alright, let's take a look at the rasterizer implementation. We are going to define an area in world space of a given size, centered on the desired quote-unquote capture location. Since the Niagara emitter is attached to the character, I can simply use its location as a capture location because I want to rasterize effects around the character. The size of this area is arbitrary and depends on several factors: how far the effects need to be visible, the render target resolution, the required texel density, and so on. Let's quickly go back to the blueprint for a moment. Remember, the effects buffer is sent to Niagara, and the appropriate rasterizer emitters are enabled or disabled as needed. One thing I didn't show is that the area scale is also sent to Niagara and updated in a material parameter collection when it's set. The same goes for the rasterizer location, which is updated in a material parameter collection every tick using a timer. In Niagara, I have a first emitter that rasterizes the effects within a defined area around that location. I refer to this as the local space rasterizer. I use 2 16-bit RGBA render targets to create a double buffer. In the first simulation stage, whatever is stored in the render target is copied to the previous render target to keep track of the effects rasterized during the previous frame. This step is necessary to output velocities, as I explained just a moment ago. Next, in the second simulation stage, I get the emitter's world position, the character's position, and extract its 2D components. Since this simulation stage iterates on the render target, the execution index can be converted to UVs. Then I convert these UVs to world space coordinates. First, the center of the texture, 0.5, has to be the origin, 0, hence the minus 0.5. Then UVs are scaled to be converted to centimeters and centered on the character's location. From there, I use essentially the same code I used in the grass shader. Now I used to sample the lookup table to get the effect data. But here I access the float buffer directly to retrieve each piece of data one by one. XY position, timestamp, duration, and so on. The rest is identical. There's the distance fade, count fade, time fade, and the accumulated displacement vector is exactly the same. That said, it's also faded out towards the edges of the render target to prevent the effect from disappearing abruptly in the distance at the boundary of the capture area. That's output to the render target to produce this result. It's moving because I'm actually moving my character around, so the effects change position relative to my character, which remains at the center of the render target. It can then be sampled in the grass shader using the XY world position converted to UVs using the capture location and scale. It's best to use the pivot's world position if possible instead of the vertex position to avoid distortion around the effect's origin. I'm also using clamp addressing to prevent the texture from tiling, and since the borders are black because of the edge fade, no offset will be sampled outside the rasterized area. The rest of the shader remains the same. And voila, the effects are rasterized around you and sampled in the grass shader. It's much cheaper than using the lookup table method, but it's also more constraining. There's no time delay along the grass length, for instance, it's spatially limited, etc. Now, one thing you might want to do is convert this render target from local space to world space. It's a concept I already explained in a previous video, so I'll keep it short here, especially since it doesn't necessarily serve any purpose in this particular case. Still, it's a useful trick to know, so I want to mention it briefly. The idea is to sample the render target at the capture location, let it tile, and render an area of the same size but positioned with its corner at the world origin. This happens in that emitter. I use a 2D grid to store the intermediate result, which is initialized here. I retrieve the emitter's world location, the capture location, just like before. Then I compute UVs from the execution index, center the texture, and offset it further to account for where the render target was rasterized in unit space. Next, with these UVs, I sample the render target and store the XYZ components in the 2D grid. After that, I create the double buffer. I copy whatever is stored in that render target into another render target, and then I update the main render target with the contents of the 2D grid. This gives you the rasterized effects in local space, now converted to world space. I'm still moving my character around, but notice that the effects don't move with me anymore. I do spawn them at different locations, but they all stay fixed in place. That's because they are now rasterized relative to the world origin, which remains fixed, instead of relative to my character. As I move, effects that are at the boundary of the local render target start to fade away, almost like a box mask is being applied around my character's world location, if that makes sense. It can then be sampled in the grass shader using only the scale to convert world space coordinates to unit space, since the capture is already cornered at 0, 0, 0. To prevent tiling, you can apply a box mask around the capture's location. And again, the result isn't visually different here. But this spatially stable render target can be iterated on additively, allowing you to keep accumulating the local render target to create a trail or something similar. A handy trick to know. Voila, that's pretty much it. I've demonstrated two techniques for creating simple effects. Each technique has its pros and cons, and both, as they are, to be honest, somewhat limited and not highly scalable. There are plenty of techniques to achieve this kind of effect, but none are perfect, so it's always good to know your options. Also, keep in mind that regardless of the technique used, Niagara offers a lot of possibilities, and what I demonstrated today can be implemented in many different ways. For example, instead of managing a float buffer, you could use Niagara's data channels to describe effects and push them to the data channel. I chose to keep it simple here by managing a float array that's sent to the Niagara system via a direct reference. Oh, and by the way, data channels is a topic I covered in a previous video, link will be up there. I hope this video was helpful. If you enjoyed it, feel free to leave a like and subscribe to the channel. And if you'd like to support me or access the project files, they're available as a tier 2 reward on my Patreon. Thanks for watching, and a big thank you to my patrons for their support. I'll see you in the next video. Until then, take care of yourself. Bye bye!